Hi and welcome to this video.
Oh, bonjour, please come in.
My name is Jan-Hendrik and in this video I would like to demonstrate how to do visualizations in R.
Asseyez-vous. Sit down, please. Là. Le fouet. Ah, inspire.
For this video I planned the following. For the visualization of data, we need to differentiate how many variables we would like to show from our data. We start with one variable, or let's better say, with its distribution. Then, of course, we go into two variables and how they are interconnected, how they interact. And a special case is time series data. Always, if you have time, especially on your x-axis, that is time series data, and that will end up in a whole new world of visualizations. Last but not least, I would like to show you how to save your plots on hard disk. Of course, you can manually export all your visualizations, all your charts, but of course you can also automatize that. In showing one variable and two variable graphs, we need to differentiate in metric data and into nominal and ordinal data. Metric data is defined as data where the distance between two units is always the same. Just like a meter is cut into centimeters, the distance is always the same. The same might be true for temperature, the same might be true for euro or dollar amounts whatsoever. So that is metric data. The opposite of metric data is nominal or ordinal data. That is always the case where the distance is not the same or where the distance is typically not defined. Group data is maybe the headline for this. So, male or female students, that will be the topic today. And of course, there is no defined distance between male and female students. That are two groups, the male and the female ones. The same is true for red, green and blue, cars or balls, whatever you like, or flowers. Of course, they are grouped and there is no defined distance between them. Ordinal data is if we have nominal data, but the order plays a role. So, for example, small, medium, large. Of course, the order plays a role. Medium, small, and large doesn't make any sense. So, ordinal data is ordered nominal data. And if we go into that, we will start with metric data and with the strip plot.
You've got me all wrong. You don't know how hard it is being a woman looking the way I do.
The strip plot is simply only one axis, only the x-axis, and you plot points on that axis. Of course, if you have many points, typically they will overlap or they will share a specific spot. So you can't really recognize how many spots do you see on this strip plot. Nevertheless, the strip plot is the very, very basic metric plot here. If you want to give the reader a bit more overview, of course, you're going to switch to the histogram. The histogram simply counts how many spots are there in a certain interval and will show this interval represented by a bar. The same is true for nominal and ordinal data if we talk of bar plots. The only difference is that the bars in bar plots have a certain distance. They are apart, while in the histogram they are interconnected or attached to each other. If we then go to two variables, we can of course have matrix on the x-axis and matrix on the epsilon axis, or we can have metric on the x and nominal data on the epsilon, or vice versa, of course. If we have metric versus metric, we use a scatter plot. A scatter plot means all those points, data points, in between those axes. If we don't have metric on one of the axes, we switch to the so-called bar plot. I will show you how to read the bar plot later on. Let us switch to our studio and I will show you how that works out. Now I have arrived in our studio, and as always, the first step is to open up a new R script window. Here it is, and to give our project a beautiful headline starting with 5 hashtags. And our headline, of course, is Visualization in R, all plots in R base 1, 2, 3, 4, 5. And of course, we need some data. And I have prepared some data. Here's the data that I have prepared. I asked all the students in my course on data science about their body length. So we see the body length of these students here in meters. We see their shoe size here in European norm shoe size. And we see their gender, if they are male or female. And we're going to use this data, of course, in R. Now let us quickly import that data. So the headline here is data import. Of course, we need a library. The library read_excel to read an Excel file. If you have not yet installed this library on your computer, you will need to do that using import.packages and in brackets and in quotation mark read_excel. But since I have already installed this on my computer, I'm not going to rerun this. I'm going to make a command if not yet done. I always do it like this because if I give this code to someone else, he or she could only use the enter key and it is accessible here, but I'm not going to run it. What I'm going to run, of course, is the library itself. So library read_excel, there it is. And now I need to read the data. I want to store it into a data frame that is called df_data. And I'm assigning this data to this data frame. So read_excel is the command to read it. We need some brackets and we need some quotation marks. And of course we need a path. Users. It's on my desktop. And desktop. And the file name, of course, is shoesize.xlsx. Let's see if that works out. Perfect. There's the data frame. 30 observations because I asked 30 students in 3 variables. And the variable name, vector length, vector shoe, and vector gender are correctly imported. I already see the first data here. That has worked out beautifully. What I need to do first, of course, is to make the gender a factor variable. So I directly access that vector inside the data frame. So df data is the data frame here. And I'm accessing with a $sign the vector gender inside here. and I'm going to overwrite it with itself, but as factor. And as I already said in another video, always if we start a command with those as dot, it's always a type conversion. So here I convert a character vector into a factor vector. And this is what I'm going to do. So tf data dollar vector gender. I run this, and I now see on the right hand side in my environment that the vector gender is now a factor with 2 levels, female and male. This is what I wanted to achieve. If we now would have order data, and not only nominal, because male and female of course is purely nominal, there is no order, then I would have to give it an order. I'm going to do this here. I can also do this with male and female if I always want to have the females first on the axis. So I just give it an order. Make female always appear first. Order the data. So I do this with the command factor. df data dollar vector gender, ordered is true, so I set this true, the ordered parameter, and I need to define the levels. Of course, the levels are, and I do this inside a vector, the levels are female, and female is first here, and male is second, so the female will always be the first on the axis, and it will be ordered data. Now, object not interpretable as a factor. Why not? Where's my problem?
The letter C. The letter C.
Oh, it's a capital C. I need to have a small cap C. That's it, and there it is. Now that's funny, of course. Female is smaller than male. Of course, don't get me wrong. That means females will always be shown first in the charts. Okay. Well, that's it. And now we start plotting. And we start with plotting one variable. And of course, as I said, it's metric data. And the first thing I want to show is the strip chart. And I now can hide away all the data import so that we don't get confused of all that code. Now, it's pretty simple. We just go into strip chart, and I want to make df data dollar, and I would like to show the shoe size. And I run this chunk of code, and there's our first chart. Not so beautiful so far, nevertheless it's our first chart, and maybe to get a first glance of our data it's absolutely sufficient. Now we see that the plot window has opened automatically, and we have this chart. Typically, if you click on zoom, you will have a better display of this chart, because sometimes it's a bit small in that tab. Now, of course, we see the problems that we have with strip charts. We see the shoe size of 30 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, seemingly, many data points share a certain spot, and we simply don't know where they are. So, a strip chart here based on the shoe size is not the best choice. Nevertheless, we can have certain variations on that, and I want to show you those variations, and they will help us a lot. So, variations. And I just take this strip chart command and I paste it here, and I just hand over another parameter, and that is method, and the method will be set to jitter. So I apply the method jitter in this case, and there it is. Now it shakes or jitters all those points, and I can now see, I just zoom in, where the most of those points are. So seemingly only one person has the European shoe size 36. That's quite small feet here. Only one person had 47. That's quite large. And many of them are distributed among. So here, obviously, 44. That's quite a number of persons. Here we have 5 on 45. Here we have 3 on 41. And we can distinguish now where those points, those data points are. But I don't like this, to be honest. To me, it's a bit very much jittered. But there's another method, and the other method is called stack. So this is what I like more. I just zoom in, and we get those data points stacked. And this is very much what is later on understood to be a histogram or a bar plot. It's simply stacked or counted data here. Now, well, those are the variations of the strip chart, and I would like now to professionalize this strip chart together with you. I stick with a stacked one, and, well, professionalization. Let's put it there. And of course, we can apply the enter after each and every parameter so that we can differentiate a little between those lines, and it's more clear what I'm doing. So the first thing that I would like to do, I would like to split between male and female students. It's quite easy to do that. I just go directly behind that shoe size vector, and I use a tilde. A tilde, like this little wave here, and that means independence of. So the shoe size should be shown independence of the gender. Let me run just this. And we see that the data is now split into male and female students. Seemingly the data is quite clear cut. I just go on zoom, and here we have the females. It is also indicated here on the left hand side. And here we have the males, which is also indicated here. And the data is really clear cut, so there's no overlapping of data. That's quite random in this case. Nevertheless, very clear cut shoe size. Well, how can we continue with making those plots more professional? Of course, we could add a main capture or main headline. Main shoe size of students. I just run this, and now we already see that there's a headline, there's a capture for that shoe size of students. I just add another parameter, xlab, which stands for label of the x-axis, xlab. And of course on the xlab or on the x-axis I would like to have shoe size. I just always give the unit, so it's EU norm. So everyone knows that on the x-axis is the shoe size and not some DF data $WEC shoe. No one knows what that is. So here we have shoe size on the x-axis. And of course, I could also add some captures on the epsilon axis, like epsilon lab, which is gender. And not to forget, I want to replace female and male by group names. Group.names. And that is, since I don't give 1 but 2, I need to hand over a vector with C again. And the vector should now be female students and male students. And I just run this. And now we got an epsilon label, gender, we have female students, and we have male students. Well, can we change maybe the color? Of course we can. So we hand over a color, and we don't only hand over one color, but we hand over 2 colors, one for the female and one for the male. So again, we need to hand over a vector, and I would like to have them in red, and I would like to have them in blue. Let's run this. And now they are colored in red and blue. And of course we can change. Now we have this little box. We can switch that using the plot character, PCH plot character, and I give it a 19 as a parameter. You just need to Google it, plotting in R PCH, and you will find many pictures where all different plot characters are shown. I like very much plot character number 19. That will be a little ball or a little point here. That looks quite beautiful. Now, I would guess this is already some kind of professional. I can work with this. This is publishable, a publishable chart or publishable plot. So it doesn't look too technical. It's quite beautiful, and we can use this one quite well. I just want to show you one last parameter. We can switch the axis now. Vertical is true, and we have the x and the epsilon axis switched.
Okay, class, please. Changez. Là.
Okay, that was our first chart, the strip chart. But as I said, this is only a very basic chart. It is not quite commonly used, but what is used a lot more, of course, is the histogram, and we already see the structure of a histogram here in the strip chart. So why not let us go into strip chart. So we want still to plot metric data, and we want to have a histogram. And I fold away the strip chart, and it's quite simple, and it's just hist df data dollar, and now I use the body length. So the body length, let's look at my student's body length, and there it is. So here's our first histogram. It's automatically chosen like it is. So seemingly we have 2 students that are between 1 meter 60 and 1 meter 65, 3 students between 165 and 170, 6 students between 170 and 175. And let's take a look here. This is my size, so 7 of my students are roughly around my body length here. Beautiful, beautiful. Well, of course, we can make several variations of this plot. So let me copy this. Okay, so what else can we do? Of course, we can change the number of breaks. I just give the breaks, hand over the breaks parameter, and I just want 4 breaks. Let's run this. And there we have now 4 bars that show the length with 10 centimeters between. We can apply the brakes parameter in a different way. I just want to show you that. I can choose on my own where to set the brakes or where to define the bars. So brakes, and I hand over a vector of brakes. So like 150, 160, 170, 180, 190, and 2 meters. Did I do that correctly? We will see. I just run it. And there it is. Let's zoom into that one. Now we have the brakes just defined by me, and since I defined 150 and 160 as a brake, but no data point is in there, we see a bar of 0 here, and all other bars are defined as I wanted it. So you can define that part of the histogram completely on your own. What else can I do? I can switch the histogram from frequency to probability by setting the frequency parameter to false. And now I see on the left hand side not frequency anymore. I just go back to the last one. There was frequency. Now we have density. So we seemingly have a different unit here, a different unit. Of course, we can also professionalize our plot here. I just take the one with the brakes, and I want to professionalize. Okay. So let's give it a headline. So a main capture will be length of students, or let's say body length of students, right? Body length of students. Of course, we can give it labels. XLab will be... What happened here? So, XLab will be body length in centimeter. That was the error here. All right, so we have body length in centimeters and we have frequency. If I want to change that, of course, I can give it an epsilon lab, which is frequency, and let's put it like that. But we all know what happens here. Of course, I can switch the color just by handing over the color parameter, dark magenta. By the way, you can also look up, like on Google, R plotting colors, and you will find many pictures of the color coding. So you can choose whatever color you like. And let's run this. And that's quite a bit, well, a bit too much, isn't it? A bit too much color. That's why I like very much the density parameter. And just set the density to 10. And we will have it like this. The density of 10 means that we have 10 lines per inch of plot. And we can zoom into it, and it looks beautiful, printing quality, and you can use it for your publications or for whatever you like. The next plot that I would like to show you is the distribution of nominal or ordinal data. We would like to go into the bar plot. So 1, 2, 3, 4, 5 are nominal or ordinal data and the bar plot. I just give it a bit more space here. Well, the bar plot is based on the table command. So if I apply the table command and I would like to count how many male and how many female students, so the vector gender, I can run the table command and I get the answer that in my course there were 11 female and 19 male students. And I hand over this table completely to the bar plot command. So I insert this table into the bar plot command and run this, and I will get this bar plot here. We don't see any x-axis since there is no real measure on the x-axis, but we see the groups female and male students, and we see the frequency on the epsilon axis. Of course, we can professionalize that, and we can also make variations. One of the most common variations here, of course, is to switch the order of the axis. So I go into it and I use horiz for horizontal and set that one true. And now we have the vertical bar plot instead of the horizontal instead of the vertical bar plot. Now let's professionalize all that. Of course, we can give it a main capture. We can label the epsilon axis. We can label the x-axis. And we can run all that, and we have already a quite professional plot here with main capture, gender on the x-axis and frequency on the epsilon axis. What else can we do? Of course, we can change the names or the group names. That would be the names.arg for argument. And of course, I have to hand over a vector again with female students and male students. Let's run that. And there it is. We just changed from just female to female students and male students. We can give different colors. Oh no, of course we need to hand over a vector. Again, red and blue. We can use the same idea with the density to make it more beautiful. And let's run this. There it is. We have a red bar and a blue bar for the female and the male students. And last but not least, I would like to show the epsilon lim to set the limits for the epsilon axis. Sorry for that. Equals, and of course I now need to set a lower bound and an upper bound using a vector, and the lower bound should be 0, of course, and the upper one should be 25 and not only 15 anymore. And let's run this, and now we have just repaired the epsilon axis. That looks much more better now. Well, quite professional. I would use it like that. So there's no need to immediately switch to ggplot or other packages. We can professionalize standard plots too. Now, we come to our second headline for today, which is plotting two variables. metric versus metric is the first, and that will be the scatter plot. 1, 2, 3, 4, 5. I just remove all the old code here and we start over. So, scatterplot. Just use the plot command and we now hand over the data, df data $, and I want to plot the shoe size, and that's quite interesting here. Independence tilde. If you don't know how to do the tilde, on my keyboard it's the Alt-GR and the plus sign. But that's of course depending on which kind of keyboard layout you will have, if you have a German or English or whatsoever keyboard layout. But it's the tilde, it's this little wave. So independence of df data $, and of course independence of the body length. So I would assume that a larger student will have a larger shoe size. That's my idea. Maybe I'm wrong, but let's have a look. And there it is. So seemingly there is a quite good explanatory power of the body length to the shoe size, and this is really real data. This is not I really collected this data in my course, and seemingly with some jittering or whatsoever, with some distribution, the shoe size is very much determined by the body length. Fine, nice to see it like this. Nevertheless, of course, we can professionalize that too. So professionalization. I just copy the code and let's go into it. The first thing I always do is to give it a main capture. Of course I give it X label. Body length in centimeters, and I give it an epsilon label like shoe size European norm. I want to have black points. Oh, maybe I try something else here. Let me try something else. I use the plot character 21, which is a 2-colored plot character, and it's a circle, but the circle shall be black, but the background BG shall be yellow. Let's run this. Of course it doesn't work. I need quotation marks. And now I can run it.
And now back to your regularly scheduled program.
Now the camera is back and we still work on our beautiful scatter plot, and I have this swarm of bees here with little dots, with little points like black circles and yellow background. Can we have bigger ones? Of course we can. I just add another parameter that is CEX, and CEX is a factor. A factor, how many times the standard size do I want? I want to have a 1.5 times the standard size, and if I run this, I get larger points here, larger data points, and a much better view of my plot. Well, and we can add another feature, and we can add a line to this plot, because seemingly there's something like a linear relationship between the body length and the shoe size. And Accordingly, I can adopt an OLS model, a linear regression, and I can plot that. So I use appline, that's the command. It must follow directly the plot, since it will plot into this plot. And then in this appline command, I have to integrate, of course, the regression results. Well, I can do a regression using the lm command, linear model. So I have the linear model, the regression, inside the appline, which is plot command. And of course, I need to hand over the data. Just like here, like it is given here, the shoe size is determined by the body length. Accordingly, I just copy it in here. And I want another color, of course, so I give the hand over the color parameter, and that should be red. Let me add this, and there is my beautiful regression line. Let's zoom in. Yes, beautiful, great. Perfectly fitting to the points, OLS fitted, and that's a really, really great plot here. Nevertheless, I would like to show a second version of that. I just copy it. I don't use the appline again. I just copy the plot command. And I would like now to differentiate between male and female students inside this plot, differentiating the color of those little B points here. The background color here was set to yellow. And now I remove this setting and I include the if-else command. If-else is known if something happens, then this parameter is valid. If something else is happening, the else parameter is happening. So, first of all, we need some kind of condition for the if-else. And the condition, of course, is df data dollar vector gender equals, always two equivalent signs here because we want to compare. And if it is a female, then, oh, no, a comma, then the parameter should be coral1, which is simply color. So if else gives back coral if the gender is female. If the gender is not female, else it will give back cyan 4, which is another color. And that's pretty much it. So I run this, and already quite beautiful. We now have in this coral red color the female students, and in this greenish blue color, cyan color, the male students. Well, a legend would help, wouldn't it? Accordingly, we can add a legend using the legend command, and we simply hand make this legend. So it shall be on the bottom right corner. It has two instances. Accordingly, I hand over a vector with those instances. It is female, or let's put it a female student and a male student. The color here should be, of course, coral, no, in quotation marks, coral 1 and cyan 4. So these are the colors, and the plot character shall be 20. I don't choose exactly the same one. I choose a different one here. That should do. And there it is. I just zoom in, and we get this beautiful legend here. I don't think that the plot character 21 is the best choice. Let me just redo that, and let's choose 19. I run both commands, and now it's a better choice. I just zoom in, and I get this beautiful legend in the bottom right corner. Yes, that was it about scatter plots. So the next plot that I would like to introduce here, of course, is a plot for two variables again. But of course now metric versus nominal or ordinal data, and that's of course the box plot. 1, 2, 3, 4, 5. And let's start with the box plot. The very basic box plot can be easily achieved by the box plot command. And in this case, I want to see df data underscore data dollar the shoe size, which is metric, and I would like to have it differentiated or determined by the gender. So df underscore data dollar gender. And I just run this line, and there is my very, very basic box plot. It's not yet beautiful, nevertheless.
Ready, set, go.
Box. Window.
Batman.
Seemingly we can now differentiate between the female and the male students, and we see some kind of plot that shows us the shoe size. And maybe you're not familiar with box plots, so I will give you a little introduction. The data here, let's say the shoe size or the size of the feet of the female and the male students, is now split into four quartiles. The lowest quartile, the next quartile, the third and the fourth quartile, of course. The big line in the middle is the median. So 50% of the female students have smaller feet, and 50% of the female students have larger feet. The same is true for the male. We look at the big, thick line here. 50% of the male students have smaller feet, and 50% have larger feet. Everything underneath the box, that's the lowest quartile. So this line is the 25% percentile. So everything below the lowest 25%. Between this line and the median, that's the second quartile. So, right, the next group. Then inside the box, up to the upper border of the box, is the third quartile, and the largest 25% are above that box. So this is the 25% percentile, the 50% percentile is the median, and the 75% percentile. The lowest 25% are below, the highest 25% are above. So that's the box. Then we should take care about the whiskers. The whiskers typically go down to the lowest value, so the lower whisker, and the upper whisker normally goes up to the maximum, to the highest value. But there are exemptions. The length of the whisker is restricted to 1.5 times the interquartile range. The interquartile range, by the way, is defined as the distance between the 25% percentile and the 75% percentile. So the length of this box. So if you multiply the length of this box by 1.5, that's the maximum length of the whisker. It cannot be longer. If there are data points outside 1.5 times the interquartile range, so if the whisker is not long enough, there will be dots. Currently we don't have those dots in this data set, but sometimes you see dots above or dots below. Here is the same. Sometimes you see dots below and dots above. Why that? Because those dots are assumed to be statistical outliers, and that's why they are shown individually. While normally the whiskers go down to the minimum and up to the maximum, but they do not go lower or higher than 1.5 times interquartile distance or interquartile range. Well, that's it. How to read the box plot. So it's simply dividing the group into 4 subgroups, the lowest one, 2 medium groups, and the largest one. Okay, of course there are variations. And I copy this basic box plot here. I put it in there. And the first variation, or the only variation that I would like to show, is with the parameter notch is true. If I run this parameter notch is true, I can just show you. But maybe you already recognized it, that I received a warning message here. So this warning message wants to tell me there's something wrong, and that's due to the data. That's not due to the function. This notch goes below the lower border of the box, and that's why we received this message. Well, those notches, very interesting. They give an idea if those medians that we see, so the thick lines, if they are comparable or if they are significantly different. Because if those notches do not overlay, if they are like this, right? We can say that these medians are significantly different. We see a significant difference between the 2 medians. Here, this is the case, because the medians between female and male shoe sizes are so far apart, they are not comparable. If they do match, so if they are like this, we can't tell anything about the significance. Possibly they are different, nevertheless, we can't support this hypothesis based on the data. So to have this significance information at hand, those notches are quite nice to have. Well, can we professionalize this? Of course we can. So again, I copy the basic box plot. I don't want to have the notches. And of course I add some parameters like my main capture. This is shoe size of male and female, well, let's say female and male students. I add an X label. The X label shall be gender. The epsilon label shall be shoe size. EU norm, of course. By the way, I always put the unit into the access labels, because otherwise no one would know what is that. 36 to 46, no one knows which kind of shoe size that is. That's why I put EU norm here. In the US they have a different norm. Even in Italy there's a different norm, and that's why I add this information into the label. Okay, let's run this. Now that already becomes quite more professional. Nevertheless, I can do more than that. I can give names to each and every box plot. Yet there is female and male. I can write female students and male students, but of course I can't do it like this. I have to give it as a vector. So adding that with, or wrapping that with the C command. And I want to have them in different colors. Again, I hand over more than one color, so I have to wrap it with the C, the combine command. So I choose dark red and dark blue. I run that, and there it is. Now let's zoom in. We now have female students here and male students here, and I have a red box plot and a blue box plot to differentiate the colors. I could add a legend now. I just don't want to take too long to do this. Well, that's it about box plot. Last but not least, I would like to show you time series. So for time series data, we need a completely different set of charts. Why that? Because if we have the time on the x-axis, we should show that. We should make that clear to our reader that this is a time plot. And that will always be done by lines, by connecting lines. So we don't show individual dots, but we always show lines. And the very basic plot here, of course, is the line plot. I hide away all the other plots here. Well, we don't have time data, so we need some time data. I create some data, and it shall be a time series data, but I don't make it a time series yet. I make it a vector so far. So this is a vector, again with the C. And I run it, and I see in my environment that there is my vector. Now I have two choices. The first choice is to misuse the plot. So I plot simply this data, TS data. I could run it now, but that would be a normal scatter plot. Since the computer doesn't know that this is time series data, it just makes a scatter plot. That's it. I can now add the type parameter and give it an O. Giving the O, it will turn the scatter plot into a line plot. So if you want to know about all those parameters, you can just watch the documentation about the plot command by question mark and plot. And now let's have a look. The default scatterplot function, that's the default scatterplot function, and there, for example, is the type parameter, and each and every type that is available is explained here. So let's run it. And there is our line chart. So this is without any type conversion. So if I write without any time conversion, there must be a version with type conversion. And I copy it, and I remove the type parameter. But what I do, I convert the vector into a time series. And to convert it, I use the TS command. Now, inside here you see that I apply the TS command to turn the vector into a time series object. And if it is a time series object, the plot command already knows oh, it's time series data, I need to plot a line chart. It looks quite the same, but we see that time is given here on the X label. Of course, you can also professionalize all those time plots, no problem. It's quite the same. Okay. If I now would like to save one of my plots to the hard disk, again, I have two choices, or even three. I could go here to the export button manually, click the little pull down menu, and there is save as image. We're going to go into that. Save as PDF, which is quite the same, just another format, or copy to clipboard. Copy to clipboard, of course, is the most easy one. You can change the width if you like to. You can change the height if you like to. You can update that preview. You can choose if it shall be a bitmap or meta file. I would always recommend to choose meta file here, and then you can copy the plot. Meta file can be scaled a bit better. And if you then go into your Word or PowerPoint or whatever you like, you can simply insert that plot in there, scale it a little. It does not become worse, as you see, so the quality is quite good here. And there it is, of course. That's the most simple way how to use those plots and how to export them. The second version, of course, is to go to the export and save as image. And here you can choose whether it should be a PNG, JPEG, TIFF, BMP, meta file, SVG, or EPS. Again, you can scale it differently with width and height. You can choose the directory, you can choose a file name, and you can save it. I don't want to go this way. I want to show you the third way, how we could automatize all that. So, there's one point. We need to open a channel to a file. And we need to close it. And that's very important. Don't forget to close it. So let's start with that. Open a PDF. I start with PDF. Open a PDF file. And we do that using PDF. And of course we need to hand over a path to a new PDF file. So my new PDF file should be found on hard disk C, users, my name, on my desktop, and its name should be plottest.pdf. And I just run this. Now the file is open, and everything that is getting plotted now will not be displayed on the screen, but it will be plotted into this file. So let's do that. Of course, I need a beautiful plot. The scatter plot was so beautiful. Let's do that. The one with the app line, for example. I copy this code. And I just put it here. And I run those two lines. So I just plotted this plot. And as you see, there is no output on the screen because it is redirected into the file. And now I have to close the file. And that's always device off with brackets, and that's it. Now let's have a look what's on my screen. It's on my desktop, of course, and there is plot test. I open it, and of course it's a PDF file with this beautiful plot. There it is. Well, PDF is quite uncommon for plots, but we can apply the same. I just put it into some comments here. You can do this using PNG, you can use it using JPEG. So just replace this PDF here with PNG, JPEG, PostScript, BMP, or WinMeter file. And with those commands you can open files of different formats, you can plot into those files, you can close those files, and you will have them saved on your hard disk. That's it for today. Thank you very much for watching this video. See you in the next video.